Okay. So first question is a true false one. So I will use the poll for this. The first one is if D-fructose has an optical rotation of negative 92 degrees, L-fructose should have an optical rotation of positive 92 degrees. And you don't have to know the structure of these, but just based off of these names and like something, a term in it, like you should be able to figure this out. Okay. Okay. So 9 of you said true and 4 said false. The majority here is good. This one is true. And it's true because these two are enantiomers. So like D versus L of the same sugar are enantiomers. That's like, I can draw D and L glucose, and actually I won't do that right now because we're gonna draw D glucose later, but like if you like Google D fructose and L fructose, you'll see they're exact mirror images. Like if you look at every chiral center, they're opposites. So I'm not drawing it here, but like just as an example of some random sugar. This is an L form of it, and then actually I won't draw an arrow, but if you were to draw the enantiomer, it would look like this. Just at every chiral center, it's the opposite configuration. So, oh, that was wrong. It's the opposite configuration at every chiral center. It doesn't matter how many there are. It's just the reverse at all of them. So then these are enantiomers. And then the only thing that distinguishes enantiomers is they have opposite polarizations of light, which is what this question is saying. So I don't even know if this number is correct. I might have just made it up when I made this question, but like whatever the number is, like if it's positive something for one enantiomer, it's going to be negative same number for the other one. And this is something from 112A that you should be aware of. Okay. And then one more here. Most naturally occurring carbohydrates are D sugars. Is that true or false? Give it 10 or so more seconds. Okay. So most of you said this is true, and that's correct. This one is true. There's not really any logic to this that I know of. That's just how nature does things. So you should just memorize the most naturally occurring sugars are D. L sugars do exist, so like you should be able to draw them and identify them. But like if you're asked true or false like this, D sugars are more common. Okay, so that's question 1. I'm gonna go ahead and erase the screen and move on to the next one so I can have more room. But if you have a question about this or anything, feel free to stop me. So here I'm asking to rank these compounds in terms of their base strength. And all of these have an amine attached to benzene. So the only difference is what's at the para position here, and that will affect the base strength. And there's like some general ways you can look at these to like figure out how strong or weak the bases will be. Can anybody tell me what an EDG is going to do to the base strength? Yeah, we'll make it a stronger base. So EDGs make stronger, and then EWGs do the opposite. They make bases weaker. So in general, you can think of it like that. And if you have a hard time remembering this, just remember like what a base is. Bases have a lone pair and they like to donate it to acids. That's close. I'll get to that in a minute. I just want to explain like these trends a little quickly. But yeah, so bases want to donate electrons. Bases. So if you have an electron donating group, then that will give more electrons to the thing that's trying to donate electrons. That's why it makes it stronger. And then if you pull electrons away with a withdrawing group, then it has less electrons to donate, so it's weaker. So just remember this basic definition of a base that might help you remember which one is which. And then when you're looking at benzene acids and bases like this, I think it's a really good idea to put this little reaction arrow for trends. Like either write it down or have a mental note of it. I would write it down, but you can do whatever you prefer. And then put the different substituents on it, because that kind of helps you visualize it. So we'll start with this ketone here. Where does that fall on it? Yeah, it falls on the left. Once we like put them all on the arrow, it'll probably make more sense what the answer is. Okay, the carbonyl is going to be on the left. And okay, so like it's going to fall in this group, but relatively where in this group, like towards the right end of that circle or left, yeah, towards the right. It's kind of on the weaker side of these withdrawers. So here's the carbonyl. How about the ethyl group? Yep, left end of the right side, basically. It's an alkyl group, so you can call it an R group, it shows up there. What about SO3H? Yep, far left. It's one of the stronger withdrawing groups. And then where's bromine show up? In the middle. So stuff over here are, well, I guess I can put it like this, like stuff on the left side are electron withdrawing groups. Stuff on the right is electron donating. So these are EWGs. These are EDGs. So in terms of going from strongest to weakest, you can basically go from the right side of the arrow to the left side. The thing on the right is the strongest. The thing on the far left is the weakest. So yeah, then it's 3, 1, 4, 2, because the alkyl group is strongest, and then the bromine, and then the carbonyl, and then the SO3H group. NO2 is also far left. It would be here. I had a worksheet around the beginning of the semester. I don't remember what number it was, but it was one of the first 5 probably. where I had like the first question was sort of a fill in the blank on this arrow. Either look at the answer key or watch the recording. Okay, yeah, worksheet 5. So you can look at worksheet 5. I kind of generalized different groups so you don't have to memorize where every single thing goes, but there are a couple I think you should know. So that's a good reference for that. Yeah, this is how this would go. And just remember, in the event, which is very possible, instead of having an amine and you're asked to rank the base strength, you have like an alcohol or a carboxylic acid. Like then you'll be asked to rank these in terms of their acid strengths. And then just remember like these trends like EDGs making bases stronger and EWGs making them weaker are reversed. So like if you're looking at an acid, an EDG makes it weaker. EDGs make acids stronger. So just remember that the context is important. Like if he's asking you about bases or acids, it affects what makes it strong and weak. And these two kind of go hand in hand, but just don't forget the difference. Okay, again, I'm gonna erase the screen before I go on to the next one. So are there any questions about number 2 before I do? And like, it's perfectly okay. If like you didn't understand any part of it, I can explain it again. But if not, keep going. Okay, well, as usual, let me know. I'll go back if you had a question. Okay, so here we're looking at carboxylic acids and we're like ranking them in terms of their acid strength. So this is a case where like EDGs now make them weaker, or yeah, they make them weaker. And EWGs make them stronger. Yep, that is correct. And that has to do, this one is less like EDG versus EWG. It more has to do with the number of chlorines and where they are. So like that's the only difference between all of these. This one has no chlorines. So because that has no withdrawing groups, this one is the weakest since it has a lack of withdrawing groups, which make acid stronger. And then a general rule, which like you guys in chat got, but I'm just gonna make sure everybody knows, is like more of, or I guess I should say like the more of a group stronger effect is. I don't know if that's a very good way of describing that, but like this one has 2 chlorines on it, and this one only has 1. So the one with 2 chlorines, like it has more withdrawing groups, so it has a stronger effect. That's why this is the strongest acid, because it has more withdrawing groups. And then when you're comparing the last 2, the further away a group is, the weaker its effect is. Yeah, the one in the alpha position is stronger than the one in the beta. Because like the farther away it gets, the less pull it has basically. So then this is stronger than this. I'll also write that down. And this always applies. So regardless of if it was an EDG or an EWG, like the further away it is, the weaker its effect, the more of it there is, the stronger its effect. So these are general ideas. that can help with a question like this. And the final is cumulative, as you probably know. So like everything is fair game. But I will say, like, I'm assuming you'll have a question on at least one on like something like the last question where you're looking at amines and you're ranking their base strength, just because that's more new. You haven't been asked about that yet. That doesn't mean you won't get a question like this on a carboxylic acid. It just means I feel like you're almost guaranteed to get something like number 2 with amines. I could be wrong. I just think he'll ask about it. So just remember how bases work. Okay, go ahead and erase this as usual. Tell me to go back if you had a question. Here we've got a bit of nomenclature. Again, everything is fair game, but you just learned about amines. So if you're going to be asked to name something, I'm assuming at least one question will be on amines. This is good to be comfortable with, but everything else is too. So we'll start with this first one. I think a good place to start is numbering the structure, like choosing which ends to number from and then where to go from there. So I'll go ahead and give you some letters. Where should we make position number 1 here? C, yeah. And why should we pick C? This is correct, just why? Yeah, because of the alphabet. That's a funny way to say it, but it's true. If you numbered from here, then like you'd be giving a methyl group to number 2 instead of a chlorine, and C comes before M, so that's why you number from the side closer to the chlorine. And regardless of which side you choose, the amine is number 3, so that doesn't matter. It's just C versus M. So that's the numbering. And then we might have some stereochemistry to worry about. You might not necessarily, like you can be shown dashes and wedges, but it doesn't matter sometimes. So it's always good to make sure. So first, let's look at position 4 here. Is this a chiral center where we can determine stereochemistry? And why is it not a chiral center? If there's 2 methyl groups. So anytime there's 2 of the same group, it could be a methyl group or 2 hydrogens or 2 alcohols, like it really doesn't matter. Just as long as there's 2 identical things, it's not chiral, so you can't determine R versus S. So make sure, like if you're shown a dash or a wedge, that there's not identical groups, because that's a curveball he likes to throw. How about this one? Is this Hyrule Center? Yep, it has an amine, isopropyl, and then it has the ethyl group of the chlorine and the hydrogen. So we can and we have to show the stereochemistry here. Because if you're asked to name a molecule, the stereochemistry is an important part of it. If you don't put it, you'll lose points. And when you're determining stereochemistry, you have to go back to those Conning-Gold-Priolog rules, where like basically things of a higher atomic number get a higher priority. And then if you can't determine it based off of the first atom, you look at the second one, and then you go back to atomic number. Like, it sounds more complicated than it is, I think. Basically, just writing it down so it's on the screen. So basically, like if we're looking at this one, I think the number one priority and number four is easiest. It is, yeah. But I'll go through the whole reason of why, just to make sure everybody's on the same page. You're correct, so. Which one is number one here? I think that's usually easy to identify. The amine, yeah, because nitrogen has a higher atomic number than hydrogen or carbon, because the other things here are carbons. So this is number one. And then which one is number four? The hydrogen, yeah, because hydrogen has the lowest possible atomic number. Cool. And then the other two are carbons, so that's when the second rule comes in. Like you can't determine it by looking at those, so you kind of have to like cross that common denominator out and then look at what's attached to those carbons. So on the right side, we have a chlorine and a methyl group, and on the left side, we have a methyl group and a methyl group. So yeah, the chlorine has a higher atomic number than carbon, so that gives it a higher priority. That gives it number two. And then the left side is number three, because the hydrogen is number four. And then once you've numbered these, you draw an arrow from 1 to 2 to 3. So it would look something like this. It's going counterclockwise. So it looks like it's S because it's going counterclockwise. But one other thing besides all of this numbering and drawing an arrow stuff is you have to pay attention to where the number 4 group is. If it's anywhere but on a dash, then you have to flip what it looks like. So here the hydrogen is on a wedge, so it's not on a dash. So we have to flip it. So this looks like it's S. It's R because the hydrogen is not on a dash. Would we consider carbon 2 chiral? Yeah, that is a chiral center. So, and like it's very possible if he asks you to identify like chiral carbons in a molecule, it's good to be able to do that. But unless you're given a dash or a wedge, you can't tell if something is R or S, even if it's chiral. So we don't have to worry about it for naming it. Yeah, but yeah, it's good to make sure that is a chiral carbon. So if the 4 group is anywhere but on a dash, stereochemistry looks like. And a lot of the time, number 4 will be a hydrogen. So it might be good to draw it in like I did because it's not explicitly shown to you if it's a dash or a wedge, but you can figure it out by looking what else was there. So this is R. I'm gonna erase these because it was a bit cluttered. But this one's R. That's the numbering. So how should we name this molecule? Can put what you think it is in the chat. If you're comfortable. If not, I'll walk through it still. Oh, that's pretty close. Yeah. What a couple things. The free R, there's nothing wrong with it. I don't think you take points off, but I'll get to that in a minute. The free R, I don't think you'd lose points, but it's not necessary if there's only one chiral center. So yeah, that's one thing. I don't think that's an issue. I just want to say like, you don't have to put it. And the other thing is it is like the amine is the only functional group that's important for like a parent chain. So we wouldn't want to use amino. We only use amino if like there's a carboxylic acid or any other carbonyl, because then we use amino to like describe a functional group. But otherwise we use the amine ending. And then yeah, it'll be something along the lines of that second one. So just remember that amino is substituents if there's a carbonyl as well. Otherwise, you use the amine ending. But the numbering was good, and yeah. R 2 chloro 4 methyl 3. The exact way you do it, like this is a little different than the answer in the chat, where like it was said pent-free amine. I think either way is okay, whatever you prefer. I'm pretty sure like if you Google either of these names, you'd get the same structure. So yeah, that's just down to preference. Okay. Oh, I didn't know Canvas was down. Yeah, I can start posting recordings there. I might not be able to do all of them, but I can start doing that. And if anybody, actually I can check too. I didn't realize Canvas was down. That's bad timing. It's kind of dumb. Oh, okay. Never mind then. That's good to know. But if it goes down again, like you can let me know and I can post a recording or answer key somewhere else, like if you really need it or something, because your time is precious right now. Anyway, next one has another amine. So I'll go ahead and do the same thing I did before. Let's do this. Where should we start numbering? Which one should be number one? One person saying A, one person saying C, person saying D. Lots of mixed answers. How about, yeah, no, it's okay. So I guess there's a bit of confusion on this, and that's okay. Nobody said B, so that's good. It was not B. Because this is like a methyl group, so that would make the chain shorter if we started there. It won't be D because in terms of numbering, like this is going to be a substituent since this is 2 carbons compared to how many carbons we have on the left side. That's more. So like this will be a substituent, not the parent chain. And then for A versus C, it actually could. Oh, never mind. Yeah, no. So you prefer C because that gives number 1 to the amine, and then it gives the same number to the methyl group that you would get if you started with A. So that doesn't make a difference for the methyl group, but it gives a higher number to this, lower number, which is what you want. And then you would number it like this, because this gives a higher total number than if you were to go down here. Okay. So we have a methyl group here, and we have an ethyl group here attached to the amine. And then we have 5 carbons, and we have an amine as our functional group. So how could we name this one? That's pretty close. You don't need the second N. That's the only thing wrong. So the N-ethyl is like putting a number. That's to say the ethyl group is on the nitrogen. And then you put the free for the methyl group. Yeah, that was really close. And I don't think that would be that much of an issue in the test. So kind of color coding. That's where that stuff came from. You would have to put multiple N's if there were multiple functional groups or like multiple alkyl groups. So like say I had this structure here, then you would want to put like N for the ethyl group and then N for the methyl group and then the isopropyl one. So just really quickly as an example, like this would be N ethyl, N ethyl, and then so I mean this comes from here, but then you have a second N because you have a different functional group attached to the nitrogen. Or if you had 2 of the same one, you would put like NN dimethyl or NN diethyl or whatever. So yeah, it's similar to like if I put another methyl group here, then we would have put free, comma free dimethyl. You have to put the N twice if there's 2 of the same thing. But if they're different, then you would do it like this. So it's lots of good questions. Is there anything else about these conventions before I move on? It's good to hear. Let me know if you want me to go back. I will, if not, keep going. So number 5 is asking to draw the acyclic, which is another word for linear, just like the Fischer projection form of D-glucose, which is the only sugar structure that you have to know. All the other ones you don't have to know by name, but you should know this. And then it says to identify the configuration at each chiral center. So how many, or I guess first, like what kind of functional group does glucose have? Like, is it an aldehyde or a ketone? It's an aldose. So it should have an aldehyde at the top. No worries, like just make sure to note for the exam. So yeah, it's an aldose. And then how many carbons are there? 6, yeah. So if there's 6 carbons, that means like one of them is the aldehyde, and then you have 1, 2, 3, 4 carbons that are chiral centers, because now there's 5 total. And you have the alcohol at the bottom, so that's 6. So that's the backbone. I'm already telling you it's a D sugar, just from the name, so you don't have to necessarily memorize this one, because that's kind of just given by the fact that it's a D sugar. But going from top to bottom, like what is the orientation of the alcohol? Like, is it on the right or the left? I guess I can go one at a time. Like, what's the one at the top? Right, yeah. And then what's the next one? Left, yep. And then what's the last one? And if you're struggling to rationalize like how to memorize this, that's what I would suggest. Just like focus on the alcohols, and actually like I would just focus on like the facts that it's an aldehyde and like the orientation of the alcohols. And if you remember the orientation, then you also remember that there's 4 carbons, so you know that it's going to be 6 carbons total. And then you have the whole thing memorized. So you can look at the hydrogen if you want, but I always looked at the alcohols, and then you can just say that it's like right, left, right, right. That's the glucose. That's, I think, a good way of looking at it. And most of you will be taking biochem, so you'll have to look at more sugars. So I think looking at it that way is a good approach, just as a tip for the future. Yeah, I know. It can be fun depending on who you have it with. But okay, this is the glucose. So the D one is the one above the last one, yeah. So it's always going to be the bottommost chiral center, which will be right above the very last alcohol. And then if it was L, then it would be on the left side for that last one. Mhm. And then in terms of the configuration, it's going to be like the same kind of stuff we were doing on the naming earlier. You use those conical prelog rules, and then like higher atomic number gets higher priority. So we can look at these one at a time, but I will say there's a bit of a sheet of sugars. If you haven't caught on to it, I'll point it out. But first, we'll look at this chiral center. So to be able to determine if this is RRS, you have to be able to interpret these drawings. Are the stereochems alternating? Not quite. Not from like bottom to top, it's not alternating. But okay, so in terms of Fischer projections, like I'll just draw a random example, something like this. So the top and bottom ones are always opposite. Maybe, I'm not sure if that's a pattern. So this is how you can interpret Fischer projections. Like this Fischer projection is equivalent to a drawing like this. So the horizontal lines are wedges, and the dashes are on the vertical lines. So this is always how you can interpret these. And if you want to draw all the chiral centers, like you could redraw the structure with the vertical lines being dashes and the horizontal being wedges. That's perfectly okay. That helps you with it. I'm not going to do it with this structure, but you can do that on a test to make you comfortable. So that's how you should think about it. And then you should consider the atomic number of everything attached to a chiral center to like determine the numbering. So let's look at this one on the bottom first. Which group is number 1? The alcohol, yeah. Because that has an oxygen directly attached, and everything else is a lower atomic number than oxygen. And then what's number 4? Yeah, the hydrogen. So those are always the easiest. And then in terms of figuring out which one is which for like 2 versus 3, you have to like look at what's attached to each atom, like from here. So like up on the top is a carbon and on the bottom is a carbon. So I like to think of it as like crossing out the things that you have in common. So we crossed out the carbons. Then you have an alcohol on both. So you can cross that out. That's something in common. But then on the top, you have one more carbon. So yeah, because like the bottom chain ended at that alcohol, but the top one keeps going, there's another carbon. So that gets number 2. And then the bottom is number 3. So then you draw an arrow from 1 to 2 to 3. It looks like this. It's going counterclockwise. So it looks like it's S. But remember, on a Fischer projection, the horizontal lines are wedges, like I showed down here. So because horizontal is a wedge and the hydrogen is horizontal, then you have to flip what it looks like. So this looks like it's S, but it's actually R because of the hydrogen being on a wedge. And this is always going to be the case for carbohydrates because you'll always have a hydrogen on a horizontal line. So if you would like to memorize, like it's always like that for sugars, where you flip the stereochemistry, feel free to, but be careful because it's not always going to be like that for a Fischer projection. And yeah, if this was L, it would be S, because then you just drew the enantiomer, so the alcohol would be on the left side. And then if we numbered them like I just did, yeah, it would be L. So I'll do the rest of them a little bit faster because it'll be the same principles every time. Oops, it's kind of hard to erase these. Okay, so the first one is R. Now we'll look at this one. Number 1 and number 4 are always the easiest to identify because one of them is probably a hydrogen, the other one is something like an alcohol or a nitrogen. And then again, you can use the same ideas to like figure out which side is 2 and which side is 3. So on the top, you have these 2 carbons, you can cancel those out. And then you have an oxygen here and an oxygen here, so you can cancel those out. And then you have another carbon on the top, another one on the bottom. So you can cancel those out. Then you have an oxygen on the top and an oxygen on the bottom, so you can cancel those out. And then there's the aldehyde still. So the top is 2, yeah. And then the bottom is 3. So then again, it's going counterclockwise. It looks like it's S, but the hydrogen is still on a wedge. So it's the opposite of what it looks like. Just leave that there. Right now, we'll look at this one. So number 1 is the alcohol. Number 4 is hydrogen. Same process as before. 2 carbons, cancel those out. Alcohols here, cancel those out. You have a carbon on the top and a carbon on the bottom, so you can cancel those out. This is actually a point where I guess I'll do an example. So on the top, that's an aldehyde. And when you're doing stereochemistry assignments like these, if you have multiple bonds to something, it's honestly kind of dumb, but it's just how the rules are. You can kind of interpret that as like the double bond is just having like two bonds to whatever it is. So like this is an aldehyde, so there was a double bonds there, so you can think of it as like the carbon has bonds to two different oxygens, and then one of the oxygens has bonds to two different carbons. So you can look at it like this. And if there was a triple bonds, then it would be like three bonds to something instead of two. So that's how you can interpret the aldehyde. So like you have the carbon from the aldehyde and you have the carbon of the alcohol there. So like you can cancel those out. Those are similar. And then you have an alcohol here, which is just an oxygen. So you have one oxygen crossed out, that's in common. But then you still have this oxygen. So because you have one more oxygen, that gets a higher priority because higher atomic number than the carbon down here. So that means the top is 2 and the bottom is 3. And then if you draw an arrow from 1 to 2 to 3, actually, did I do? Yeah, I did that wrong. Wait, I swear it's supposed. Okay, I'm confusing myself. Isn't 2 on the bottom? I don't think so because of the aldehyde. Yeah, okay, I don't know why I'm getting so confused. This is what the arrow should look like. It has more carbons, but that's not always how you should look at it. A lot of the time, like if it's just, I think I have an example of it later, but like if I had this, then all you're looking at is carbons. So like the left side has more carbons than the right side. So you can look at it like that, where more carbons means higher priority. But here, like it is just a bunch of alcohols for the most part, but then you have the aldehyde on the top. And what I was trying to say is like up here, like this is a drawing of an aldehyde. This is how you can interpret an aldehyde when you're trying to like determine priority. So you can cross out the carbons because those are in common. And then you can cross out the alcohol on the bottom and one of the oxygens up here. But then you still have one more oxygen. So because you have one more oxygen up here, that has a higher priority. So the top is going to be 2 still. And then if you draw an arrow from 1 to 2 to 3, it's going clockwise this time. Yep, no worries. So it looks like it's R, but it still flips, so it's going to be S. Okay. I'm not going to bother. I'll do this like orange. Let's look at this chiral center. This is number 1. This is number 4. And I won't go through that whole crossing stuff out thing again, but it's going to be the same logic as last time. the top is going to be number 2 because we have an aldehyde there. So like because of the extra oxygen compared to the alcohol on the bottom, that gives the aldehyde a higher priority. So this is how you would number it. It looks like this. It looks like it's S, so it's R. And can anybody see a bit of a pattern to this? Like based on which side the alcohol was on and what stereochemistry it had? Yeah, if the alcohol is on the right, then it's always going to be R. If the alcohol is on the left, it's going to be S. If it's not a sugar, this doesn't apply, but if it is a carbohydrate, then this is always going to be the case. Because like the carbonyl iridyaldehyde or the ketone, that's always going to be priority 1, because like if you draw this interpretation out, like it always works out like that. It's a carbonyl versus an alcohol, so the carbonyl wins. And then the alcohol is always 1, hydrogen is always 4. So every single time it works out like this. So like you can memorize that if, well, actually, I don't think he'll ask you to explain how you figured out stereochemistry. So like if you want to look at it that way, you can. I just want to point out this doesn't apply to other Fischer projections. So like this one I drew down here in the bottom left. I don't know off the top of my head what the stereochemistry is, but you shouldn't just assume because there's an alcohol on the left that it will be S. That only applies for sugars. So yeah, take that how you will. Right. Any questions about anything here before I move on? And I think I have a bit more stereochemistry later on, so like we'll get a bit more practice with this, but I'll probably go a bit faster there because I did this in a lot of detail here. But you know, if you have a question here or there, ask, because stereochemistry is important. Okay, I'll go ahead and move on. So here I'm asking to draw an example of an L-keto hexose. So first part is it's saying it's a ketose. So that means there's a ketone in the structure. Six carbons, yeah. And then which OH is on the left side? The last chiral one, yeah. So carbon number 5, yeah. So this is 1, 2, 3, 4, 5, and then 6. And then all that matters is that this alcohol is on the left. And you do have to put the other 2, but it doesn't matter which side is which. Like I could do this, or you could put both alcohols on the left, or you could do some mix of these 2. It doesn't matter. The only thing that matters here is this alcohol being on the left. And I don't think the ketone has to be on carbon 2 necessarily, but it's probably safest to do that if he asks you to draw a ketone, because I think that's usually how it is. But yeah, like this is an example. All that matters is the last alcohol on the bottom. So be able to like interpret these names and draw examples of them or assign them to structures like I did on the last worksheet. Here, got a bit of an old reaction. We're starting with an aldehyde, and with some sort of conditions, we're getting this functional group. First of all, what kind of functional group do we have, like in our product? Yeah, it's two esters, so you can call that an acetal group. And what do we need to add to an aldehyde? Yep, there's one other thing. Yeah, you should put two equivalents if it's like this. Two equivalents, methanol, and then anhydrous catalytic hydrochloric acid. So this leads to an acetal. And just because it's a bit relevant, I'm going to go ahead and draw an intermediate here. And this is one of the mechanisms you were expected to know. So it might be good to review to see like how I got here and then how you get to the final product. But an intermediate in this mechanism would be this, like where you have one ether attached, and then you have an alcohol still. Yeah, this is called a hemiacetal. And this is important because well, it's directly related to the next one. We're starting with a sugar, as you can see, and I highlighted in colors to kind of make it easier to follow, but like we have the red one and the blue one, and then we have them here in the product. And what functional group do we have here circled? We have an alcohol and an ether attached. Not an ester. Esters are, and if it was a lactone, it's okay though. Like they do sound very similar. But an ester is a carbonyl attached to an oxygen and then more carbons. So if there's no carbonyl, then it's called an ether, not an ester. It's okay though. So yeah, it's a hemiacetal because you have an alcohol and an ether on the same carbon. And we went from a linear structure to a cyclic one. So that means you did some sort of intramolecular reaction here. Right. And like, because of that, like you have the molecules you need to react already, you just need to give them the right conditions. So yeah, like you just have to put the conditions required to make these react. So that would be HCl and catalytic. Just like other intramolecular reactions I've done in the past. So this was just to show you, because this is the only reaction you have to know of sugars, you should be aware of this reaction. And remember, it's not a new one because like you formed acetals before with aldehydes and ketones. It's like the same kinds of conditions and it works the same way. You have a carbonyl and you have an alcohol and they react to make a hemiacetal. And they can keep going. If this reacts with another sugar, it would make an acetal, but you don't have to know this for this class. Just, you'll see it in biochem. So, oops. One thing about this, it's specifically gonna work like with the alcohol that I highlighted here. Like that's gonna be the only one that reacts to a large degree to make a product. And can anybody explain why? like specifically this alcohol leads to that cyclic product and not like this one circled in red, or maybe this one, or any of the other ones? Like, what's special about the product we made? How many atoms? Yeah, most of them are equatorial, but yeah, it's a 6-membered ring. That's the important part. So 6-membered. And remember, I had on a worksheet a couple, maybe like 2 weeks ago, that like 5 and 6-membered rings are the most stable. 6-membered is the very most stable, but 5 is also pretty good. So like I showed you the product of this reaction, it gives you a 6-membered ring. Suppose we started with this alcohol, then like if you number from the nucleophile to the electrophile, yeah, okay, so that's 5. Just gonna redraw that. This is 5, which is still pretty good, but it's not as good because 6 is the most stable. So this might react a little bit, and I think it does actually, but not a whole lot because that's less stable. And then if we numbered from here, if this was the nucleophile, then you'd get a 7-membered ring, which isn't particularly stable. So that's why that didn't react. And it's the same idea of the other alcohols. Like it doesn't give you a 6-membered ring. It's not as stable. So that's why only that alcohol in blue is the one that reacted. So just be aware of that. Like, I don't know if you'll be asked to like complete reactions like this, like to show a product, but like most of the time you're going to want to form a 6-membered ring. So that's how you should figure out which alcohol is reacting. Okay. I'm going to go ahead and erase this. If you have any questions, feel free to ask. As usual. Okay, so here I'm showing you alpha D-glucose and beta D-glucose and asking you to figure out which one is which and explain which one's more stable and why. So first, like, which one is alpha? Or yeah, beta is on the left. Yeah, alpha is on the right. So that's the first part, which one is which, and which one is more stable, beta or alpha? Left beta is more stable, yeah. And why is it more stable? Yep. All of the alcohols and the CH2OH, everything is equatorial. And that makes it stable. So equatorial groups. They don't have any one free diaxial interactions. Just as an example, with the alpha one, you have a hydrogen here and here. These are axial. I guess I didn't do a great job, but like I'm trying to show that they're pointing straight down. I think I'll redraw those. these are axial. And then like the drawing doesn't do it a lot of justice, but when they're pointing down like this, like they can interact a bit. That leads to a bit of steric strain, which makes it unstable. But if it's equatorial, you don't get anything like this. So that makes it more stable. So for glucose, beta is more stable because of the equatorial positions. And this is good review because it's possible, like you could be asked a question about just a regular chair conformation cyclohexane, like with no oxygen, no sugars, like just a cyclohexane by itself. You saw this before in 112A. And like maybe he could ask you like which one of these is more stable, the one on the left or the one on the right, and then like you should be able to answer this too, just like you can explain why beta glucose is more stable than alpha glucose. Yeah, the right one is more stable because the chlorine is equatorial instead of axial, so it's more stable. So like don't forget that like this concept isn't just for sugars. You've seen it before, and he might ask about it in a context outside of sugars. But if you think about it as just one idea, it's not really anything new. And what about a tert butyl? It would be similar if you mean like instead of a chlorine, if I had, oh, like if there was a tert butyl and a chlorine. Okay, I think I see what you mean. So like, if I have like this versus this. Yeah, ideally you would want them both to be equatorial, but like suppose you had this structure and like the one on the top and then you did a ring flip. So then like one of them is always axial. Then like there is a difference between these two. Like there, one of them is better to have equatorial than the other. Which one would you say is more bulky? Like the tert butyl group is more bulky, so you would want it to be on the equatorial position. So like if you have to pick between the lesser of two evils, it's like whichever one is more bulky, you want that equatorial. So yeah, good question for review. More bulky. So it could also be with like an ethyl group versus a methyl group, then you would want the ethyl group to be equatorial. So just remember, like it might not be tert butyl, it could be anything, but whatever is larger, that's what you want equatorial. And then sure. I honestly don't remember a lot of details about it beyond like yeah, basically. I think typically you're supposed to like draw the chair conformation slightly differently. So like this is how I normally draw it. And then like if you're gonna draw a ring flip, I guess I would try to draw it like this. And yeah, like whatever was axial becomes equatorial. And if it was equatorial, it becomes axial. And yeah, you're supposed to draw them going clockwise. So like I can redo the ones I did on the left. Like if you started with this, then you would end up with something like this. like everything rotates clockwise, and then things that were equatorial become axial, axial becomes equatorial. And I got a question, like the most stable form would be if both were equatorial, and yeah, ideally you would want like everything to be equatorial so there's no diaxial interactions. But if you have this structure, like it can do a ring flip kind of spontaneously, but like then everything flips. So you just have to pick the lesser of two evils. But if you were like drawing a structure and you wanted it to be the most stable, then yeah, put everything equatorial. That's the best case scenario. So yeah, all good questions. So just like as a general note, that's what ring flips are. And there is a special name for this position. I'm circling in red. Like that's where a hemiacetal is, but if it's a sugar, there's a special name for it. Does anybody remember what it's called? It starts with an A. Yeah, it's the anomeric position. So where the hemiacetal is in a sugar, that is called the anomeric position. It's good to know. And then you would call like the alpha versus beta form, they're anomers of each other. So those are terms you should know, like that one of the positions is called anomeric, alpha versus beta, those are called anomers. And then you should know like the structure of both of these off the top of your head, just like you should know what the Fischer projection looks like. But remember, beta is everything is equatorial. So I think that's not too bad to remember. And if you want a little tip, it's kind of silly. If it doesn't help you, you don't have to remember it. But I remembered which one was alpha and which one was beta, because the one with alpha, like the oxygen here is pointing down, and alpha, when you draw it, it looks kind of like a fish. So it's like the alcohol is in the ocean below, and then beta is just the opposite. If you don't want to remember that, that's fine, but that's what worked for me. So it's, yeah, or alpha is axial. That's actually probably a better way to remember it. Whatever works. Yeah, I thought it was useful. Okay, that was a lot, but hopefully it was good. Lots of review, different topics. I'm gonna go ahead and erase this. As usual, let me know if there are any questions. Like if I move on and you still wanted to ask something, just interrupt me. I'll go back because it's easier to talk about it while like we're on the topic. But if it comes up later, I can still answer. Okay. Here we have a couple different functional groups, and like this isn't a comprehensive list, but this is a good example of a kind of question you could get with functional groups. So we'll start in the top left. What is this functional group? Yep, that's a file. Oh, you could call it a mercapto too. I'm assuming both answers would be accepted. Um, it's similar to like alcohol versus hydroxy. Like you use hydroxy if it's a substituent. You use alcohol if like it's the parent chain. So yeah, I think either would be accepted. Okay. What is this functional group? This is an amine. And especially if a structure like this, if he gives you one, just be careful to like look at the carbon where the amine is attached. Because like there's a carbonyl right here, so it kind of looks like an amide since there's a carbonyl right next to an amine. But the amine's not attached to the carbonyl carbon, so it's an amine, not an amide. And similar to the mercapto, I think amino would be an accepted answer. I'd be surprised if you took points off, but like amino is what you would call an amine as a substituent, just like hydroxy is an alcohol as a substituent. So just make sure like to be aware of the difference because it is important when you're naming a structure. So just put those as little notes. How about this one? That is a phenol. It would be an alcohol, but because there's a benzene ring, it's called a phenol. Since there's a phenyl ring. How about this part? That's an amide, and then what's the last one? Carboxylic acid, yeah. So again, this isn't a comprehensive list, but you could be asked something like this. And it's one of the first chapters in the book. Like there's a whole table. It's like 2 or 3 pages long with like all the functional groups. So you can look at that to like refer to a full list of things you might be asked about. And if you're like, I know you don't have to know every single thing from that table I'm referring to. So if you're worried and you can't find in your notes, like which ones you have to know and which ones you don't, you can ask me. I don't know off the top of my head, but like you can email me, I can let you know, just so like you don't memorize everything, including the stuff that you don't have to know. So yeah. Okay. Here I've got a bit of stereochemistry practice where like we're not naming, we're just doing R versus S. So we'll start by like doing the priority numbering 1 to 4 for each chiral center. So we'll start with this first one on the left. Which substituent is number 1? Oh, I was just like trying to emphasize I was starting at the left. Which substituent? Yeah, the amine. And then what should be number 4? That's usually pretty easy to identify. The hydrogen, yeah. And then what's number 2? Carboxylic acid. Draw that. So the amine got number 1 because nitrogen has the highest atomic number. And then the carboxylic acid got 2 because like there's oxygens here, which have a higher atomic number than no oxygens on the bottom. So that's why the methyl group was number 3. So then if you draw an arrow from 1 to 2 to 3, it looks like this. It's going clockwise. So what's the stereochemistry here? It looks like it's R, yeah. But remember, this is a Fischer projection. So what does that mean about the hydrogen? Yeah, it's S. Because it's as if there are wedges here. Hydrogen's on a wedge, not a dash. It looks like it's R, so it's S. Okay. How about this next one? Which one is going to be priority one? The alcohol, yeah. And then what's number 2? Are you sure? So this is like, I know it's written in a weird way, but yeah, the top. Because it's similar to like the carbonyl taking higher priority, or no, that's not necessarily a good example, but it's like you look at these carbons, those are similar, and then it's nitrogen versus oxygen. So oxygen gets a higher number. And then the methyl group gets number 4 because that's just a carbon, nothing else. So if you draw an arrow from 1 to 2 to 3, it looks like it's S, yeah. And, well, are you sure we have to switch it? Where's number 4? It's the methyl group, right? Yeah. So you only have to flip it if number 4 is not on a dash. But in any other case, it just stays what it looks like. So because it looks like it's S and 4 is on a dash, it is S. So just remember, like on the exam, not every single time number 4 will be on a dash. So don't just assume to flip it every time. It depends on the structure. If it's a fish, or not if it's a Fischer projection, if it's a sugar, if it's a carbohydrate, then yes, you will flip it every single time because they're always drawn the same way. Like we did earlier, hydrogen is always on a horizontal line, so it's always going to be flipped. But there are cases where a Fischer projection has number 4 not on a horizontal line, so then you don't have to flip it. So just make sure to pay attention to the structure. Okay. Next one, let's start with this chiral center at the top. Which spot gets number 1? The amine, yeah. Because that's nitrogen compared to carbon and carbon, so higher atomic number. And then this is pretty repetitive with the hydrogen, it's always number 4. And then aldehyde is number 2, yeah. Well, that is what you were saying, right? Don't just put words in your mouth. Yeah. And this is, I'll go over it just to make sure everybody gets it. It's similar to like the sugar example I had earlier. So like we can redraw this since it's an aldehyde as like the carbon is bonded to 2 oxygens and then one of the oxygens is bonded to another carbon. It's like to figure out which one has the higher number, like you look at the carbon that's in common and cross that out. And then there's an oxygen here, and there's an oxygen here, and then there's another oxygen left over. So that oxygen has a higher atomic number than no oxygens left on the bottom. So the aldehyde gets number 2. So yeah, like that's how you look at this. And then if you go from 1 to 2 to 3, it looks like this. So it's going clockwise. It looks like it's R. Should we flip it? Okay, one person saying S and a bunch of people saying yes. So yeah, you're all good. This one, hydrogen is on a horizontal line, so it's on a wedge, not a dash, so you have to flip it. So the blue one is R. Now I'm gonna erase like the numbers and all of the markings on the structure. So if you want to take a screenshot, you can. I'll post a recording right after this, but like, you know, just a warning before I do this. Now we'll go over the bottom chiral center. Which spot gets number 1? OH, yeah. Number 4 is the hydrogen, like usual. And then what's number 2? Top, yeah. So if you draw an arrow from 1 to 2 to 3, it's going counterclockwise. It looks like it's S. And yeah, one person's saying it's S. Should we flip the stereochemistry here? No flip, yeah. Because the hydrogen is on a vertical line. It's on a dash, so we don't flip it. So it looks like, and it is S. So again, just remember, only flip it if number 4 is not on a dash. Erase this in a second. Go down to the next page. Okay. Here we have 2 spots where I'm showing wedges or dashes. So I wasn't asking it before, but I should have been. Like we already went over it, but both of these were chiral centers because everything attached is a different group. So like there's no duplicates. So those are both chiral. Here, is this a chiral center? No, yeah, because there's 2 methyl groups. So we can ignore that. We don't have to worry about it. Is this a chiral center? Yeah, so we do have to worry about that. And now, the 4th thing is a hydrogen on a dash. That's number 4. What's going to be number 1? This one is a little tricky, actually. So if you haven't already, yeah, it's the right side. And for something like this, like I think it's really hard to visualize. So you don't necessarily have to take my method, but I think it's a pretty good method. Like draw out everything, like draw it out as like you can kind of interpret it from the rules. So like if you have a double bond, that means that there are 2 carbons attached here. And then there's another carbon up here. And then like you can cross out things that are in common. So left side versus right side, like there's 2 carbons, you can cross those out. And then on the left, like there's 2 carbons, so you can cross these out. And then the right side just barely has more because there's 1 more carbon here. But there aren't any carbons left on the left side. So this is number 1. The left side is number 2 because it has more carbons than the methyl group on the bottom. So like if you have time and you're comfortable, I think like crossing out the common atoms when you're looking at stuff like this is a good way to figure out the priority if you're not sure. It's pretty consistent. I don't think there's a structure where it doesn't, like it proves you wrong or something. Okay, and then going from 1 to 2 to 3, looks like this. So what's the stereochemistry? S, yeah. And no flip because the hydrogen is on a dash. How about this next one? What's going to be priority number 1? Right side, yeah, the isopropyl group. And then what's going to be number 2? The left side, the ethyl group, yeah. So then going from 1 to 2 to 3, it looks like this. So it's the stereochemistry. Yeah, it looks like it's S, but the hydrogen is on a wedge, so you flip it. So it's S, it's R. And last one, is this a chiral center? Since we have 2, I'm asking. Yep, it is chiral. So let's focus on this first. What's priority 1? The alcohol. And then what's priority 2? Yep, then the right side, because the right side goes towards the other alcohol. And then the left side just has carbons. So there's that, and then hydrogen's number 4. So then from 1 to 2 to 3, it looks like this. It looks like it's R, and the hydrogen is on a dash, so it is R. Yeah. Right. Now, if you want to take a screenshot of the screen here, feel free to, because I'm about to erase the numbers so it doesn't get too cluttered. Just leave the rest of those there. So now looking here, this is also a chiral center. And it's, I'll just say like it's the same kind of priority as the last one. The alcohol is number 1, going towards the alcohol is number 2, going towards the other one is 2. And then this is free. 4. This is the arrow. It looks like it's S, but yeah, it's R because the hydrogen is on, oh, that's supposed to be a wedge. It looks like it's S, so you flip it because the hydrogen is on a wedge. Okay, that was R. All right, so like if you want some more stereochemistry practice, like if you're not comfortable after this, remember I posted a file at the beginning of the semester. It's titled like please read, and it has like some useful links. Like it has a link to my YouTube channel, and there's a link to a Google Drive folder with a bunch of 112A stuff from when I did a workshop for that. And I think like around worksheet 5 or maybe it's later, maybe it's closer to 10. But I have like, if you open the folders, they're all labeled with like what topic they refer to. So if you're looking for practice with a certain 112A topic, you can look at those worksheets. I have a bunch on stereochemistry because we spent like 2 weeks on it when I was doing the workshop. So there's a lot of practice problems there. And there's recordings for about half of the worksheets too. So like, if you're uncomfortable with this or any other 112A topic, I'm just trying to say like, you can look at that material. That might be good practice. Okay, so yeah. Now have some reactions of a bit of variety. First, we have a ketone and an ester here, and we're adding LiAlH4 and an acid. What is this going to do? Both become alcohols, yeah. And what kind of alcohol do we get from the ketone? Secondary, and then what do we get from the ester? Primary. Yep, all good. What if I did this? NaBH4 in the first step, and then acid. Then it would just reduce the ketone. It wouldn't do anything to the ester. And those are the main two ones for reduction. There are some others, but these are the two most common ones. So yeah. Okay. How about the next one? We have a carboxylic acid and we're adding a Grignard reagent. So yeah, not what we're going for. What's gonna happen here? Yep, we're gonna form methane and the carboxylate. Because like, this isn't what's happening, what I'm about to draw, so don't like put it in your notes. But like, this is what you're going for. You want the Grignard to be a nucleophile and attack the carbonyl carbon. That's usually the purpose of a Grignard. But a Grignard is also a base. It's not just an acid. It's a pretty strong base. And carboxylic acids are acids. So like, this is a bit of a review. Remember, like, acid-base reactions are always faster than organic reactions. And organic is like a nucleophile and an electrophile, like just electrons exchanging, but not like protons. But if you have acids and bases, they always react faster than anything else. So this is going to be preferred. This is going to happen faster because it's an acid-base reaction. So yeah, you form a carboxylate, and then we get methane. Okay. How about this next one with a ketone and then pH 4.5 and an amine? Imine, yeah. And why is it specifically an imine? What kind of amine are we adding? Primary, yeah. It would, yeah. So remember, this is another little bit of review, just because this can be a bit tricky sometimes. No worries. Just like to make sure everybody, yeah. It's because of the number of carbon-nitrogen bonds. So like this is the oxygen analog to that amine. And remember, for an alcohol, you look at the carbon where the alcohol is attached, and you look at how many carbons are bonded to that carbon. So like there, it's 2. So you would call this a secondary amine, or a secondary alcohol. But if you're looking at the amine, you're just looking at the carbon-nitrogen bonds, so there's only 1, so it's primary. So remember the distinction between alcohols and amines. And if it was secondary, it would form an enamine, yeah. So if it's primary or if it's NH3, you get an imine. And then if it's secondary, you get an enamine. Remember, an imine has a carbon-nitrogen double bond like this, and then just whatever else was attached. Okay. And just as a little reminder, this reaction is only and it's like to make an imine or an enamine, you have to start with a ketone or an aldehyde, and then you need pH 4.5 and an amine. It's like you couldn't do this with a carboxylic acid or an ester or an acid halide. It's just ketones and aldehydes. Okay. Gonna erase the screen in just a second. Last one on this page, we have a beta keto ester as our starting material. And we add 1 equivalent of a base and then 1 equivalent of an alkyl halide and then acid and heat. So yeah, the product will be an alpha substituted acetone. And what kind of reaction are we doing? Like, what's the name of it? The acetoacetic ester synthesis. This is what you do if you have a ketone and an ester beta to each other, and then you do this series of reactions. It's called acetoacetic ester synthesis. And the product is always going to be a substituted acetone. There are details that you should know that explain like how that happens, and I spelled the substituted wrong, but you get the idea. And I can talk about the details, but I'll do it if any of you want me to for review. But just like in terms of like jumping to the ends, not worrying about like the details of the reaction, you can remember like acetoacetic ester gives you substituted acetone. So whatever you added with an alkyl halide or OTOS, like just put that on the alpha position and then you're done. So here it was an ethyl group, so I just put an ethyl group and that's it. But again, if you want me to go through like the details kind of quickly, I can. Sure. It's just pausing to make sure you had a chance to ask if you did. So you are starting by adding a base. That's what the first step is. Bases want protons, and the most acidic proton is here between the 2 carbonyls. So that's going to be the proton it takes. And then you form an enolate here. And enolates are good nucleophiles. And we're adding an alkyl halide, which is a good electrophile for SN2 reactions. And this is a detail like that's important to remember too for this. Like this is an SN2 step. So if the alkyl halide you added in that second step was tertiary, then it wouldn't work this way because it doesn't work. Yeah, okay. If anybody else wants me to finish, I can, but I'll just say like after you add that little group, the ethyl group, the acid will turn the ester into a carboxylic acid. And then when you heat that, you lose the carboxylic acid as carbon dioxide. Again, like I can walk through that in a little more detail, but basically all that's left at this point is you lose this and then you get that product. And you lose it as carbon dioxide. It happens like in a few extra steps, but that's the idea. I'm gonna go ahead and move on, but like I was saying, like if anybody wants me to finish that, I can. Here we have a carboxylic acid, and that was a typo actually, should have put catalytic here too. So if that confused anybody, that's my bad. Yeah, this is Fischer Esterification. So it's gonna lead to an ester. And what kind of ester is it gonna be? Methyl, ethyl, propyl, phenyl, isopropyl. What kind of ester? Yep, ethyl benzoate. That's how it be named. Because we added ethanol, we added an ethyl alcohol, so you should form an ethyl ester. Okay. What is this next reaction? Starting with toluene and then adding N-butyl chloride with AlCl3. This is Friedel-Crafts Alkylation. Let's see. So there are a few things to this. How can we add a single methyl group to a benzene? That's a good question. I can show you after we do this, if you would like. Okay. So yeah, we're doing Friedel-Crafts alkylation. And remember, this is one of the 5 EAS reactions that you saw at the beginning of the semester. So like that's the kind of reaction that we're doing. And that's important because if you're doing an EAS reaction, remember that you like have to consider directing and activating effects of things that are already on the ring, like the methyl group here. So for this, where does the methyl group show up? Yeah, I understood your question. But where does the methyl group? Yeah, it's ortho-para directing. It's like over here. So the stuff on the right side of the diagram are ortho-para and activators. Which means it directs here and here. No. Is this the product we should get? Since we're adding this and Like that's where the chlorine is, so that looks like where it should attach. Well, there are more products, but if you're given a question like this on the test, like you should be aware that it like will lead to a mixture of products, but if you get this as a question, only draw the monosubstituted products like this. So like remember that, like he might ask you to be aware of that, but for this question, this would be good. But yeah, that's what I was getting at. So remember that like this is what we're starting with. This is the alkyl halide. And then the electrophile that we'll add to the benzene ring is a carbocation. But this carbocation is primary. And there's a secondary spot right next to it. So it can do a hydride shift, yeah. Because remember, the more substituted a cation is, the more stable it is. So because we go from primary to secondary, you're making it more stable. So that can and it will happen a lot, probably. So this is the electrophile. And then the benzene ring will attach to the spot with the carbocation, not to the end of the chain. So it will give you these two products, ortho and para, substituted. And you're right, it would give multiple products, but like this is all you'd have to put for this on like a fill in the blank kind of question. Okay. So there was a reaction that like, can we add bromine and then do a Gilman to add a methyl group? That could be a way. You could also, I'm gonna do it over here. Like a kind of similar approach to that is like, if you had like a bromine, like starting the same way, and then like you make a Grignard reagent out of it. And since we only want to add one carbon, something we could react with the Grignard reagent is carbon dioxide. That will add one carbon. And that leads to a carboxylic acid, which like you don't necessarily want. We want just a methyl group, but we have ways of reducing this just down to a methyl group. So you could use diba. Remember, diba is similar to LiAlH4 and NABH4, but instead of reducing it all the way to an alcohol, it will reduce it to an aldehyde. Sorry if this is getting crowded, I can redraw anything if it looks funky. And then once you have an aldehyde, you can add hydrogen and a palladium catalyst, and that will reduce it down to an alkyl group. I think the Gilman approach also could work. I just don't remember the conditions for Gilman, and I don't remember if there's any limitations with a structure like this. But I know for sure this method would work. And there is like, yeah. So there was a reaction that he skipped over. Like there's a specific set of conditions that like allow you to add I forgot what it was called. Oh, like it allows you to make benzaldehyde for Friedel-Crafts Alkylation, but he didn't cover it, so you don't have to know it. But like if you knew that, that would make this much simpler. So I honestly don't think he'll ask you to put a methyl group on a benzene ring, but if he does, for some reason, it takes a lot of steps, but this is a way you can do it. So yeah, good question, because that's a little tricky without that reaction that he skipped. Okay. So I'm gonna erase the screen in a second to make it less crowded. As usual, if you have a question, feel free to ask. Okay. Again, if you still had one, go back. Here we have an amide and we're adding HNO3 and H2SO4. What kind of reaction are we doing here? Nitration. Yeah, we're adding a nitro group. This is another EAS reaction. So we have to consider directing effects. And if there are multiple substituents, you should think about activating effects too. So we have an amide here. Where does the amide show up on the diagram? It's meta-directing and it shows up on the left, yeah. So it will point here. That's where the nitro group will go, or on the bottom, yeah. Quick question though. What if I started like this structure and I did the same reaction? Is this still a meta director? No, it's ortho-para. Yeah. And this is an ortho-para director because like if you have the carbonyl carbon attached to the ring, that's electron deficient and it wants to pull electrons towards it. And it can do that by resonance. Like you can draw this resonance form, pulling electrons out of the ring. So remember, if carbonyl is attached to the ring, it's withdrawing. But on the top in red is the same functional group. It's an amide. But this is donating because now it's not the carbonyl carbon, it's this nitrogen. And nitrogen has lone pairs, so it can donate by resonance like this. So then because it's donating, it's an EDG and it's ortho-para directing. So it would direct here and here. I'm not going to draw those, but just to say like same functional group, but different directing effects. And this isn't a comprehensive review of like substituent effects, but I think this is one of the most tricky parts, like same functional group, different effects. So yeah, hopefully that was a good reminder. Okay. How about this last one? We have an amide and a chlorine, writing hydroxide and then acid. What kind of reaction? Yeah, we're turning the chlorine into an alcohol, and what kind of reaction would you say this is? NAS, yeah. It's going to be a nucleophilic aromatic substitution. And there are some requirements for an NAS reaction, which you should be aware of. In this case, they're all met, so it does work. But while I'm drawing the product, what are some things? Yeah, that's it, actually. You need a leaving group, which is always going to be a halogen for NAS. And then you need to have a strong electron withdrawing group, ortho or para, to it. So amides are EWGs because it's the carbonyl like this attached to the ring. So that's an EWG and it's para to the leaving group, so that works. So just remember that NAS requires strong drawing group, ortho or para. Which is a halogen. And then it uses conditions similar to this, like either NaOH or it could be like an alkoxide, like methoxide for the first step and an acid for the second step. And then maybe there's some other nucleophiles you could use, but I think like these are the main two you'd probably see. Maybe review your notes to see like any other potential ones, but like these are the main ones I think about. And the conditions are not conditions, but like the EWG is important. No, you don't have to know the mechanism for this. Good question. Just know the requirements. Okay. Again, if there are questions, I'll go back. Otherwise, go ahead and start this one. So this is a sort of fill in the blank one where you're either filling in the reagents or product. For the first one, yep, we're doing a Wittig reaction. And the conditions are with a phosphorus elide like that, yeah. So you have 3 phenyl groups attached to a phosphorus, and then that is attached to an ethyl group. Oh yeah, that's good, okay. And then I think a solvent might be CH2Cl2 dichloromethane. I don't think this is one where it's super important to have the right solvent. It might be okay to just put this. So yeah. And we recognized that it was a Wittig reaction because like we're turning this aldehyde into an alkene. Okay, yeah, that's good confirmation then. The solvent isn't necessary for Wittig. Yeah, aldehyde today or ketone to is a Wittig reaction. And it uses a reagent like this. The only difference, like this will be different depending on the alkene you form. If it was just a methyl group on the alkene, then it would just be like CH2. If it was free carbons, you'd put free, like it just depends on what you're trying to make. All right. Now we want to go from this alkene to a carboxylic acid, and we're losing 2 carbons in the process. We're losing the carbons at the top. So losing carbons and making carboxylic acid. Yeah, we have to use KMNO4 to cleave it. and what other parts of the conditions are important, like KMNO4 and yep, H3O plus. And this is important just because you've seen KMNO4 in multiple contexts. So like the conditions you use with it will slightly change how it behaves. But if you want to cleave an alkene with KMNO4, this is how you do it. You also get a byproduct from this. You get this as a byproduct, acetic acid, because that's what happens when you cleave this. You get an ethyl carboxylic acid. But yeah, that's what you need to do. And then we're going from carboxylic acids to esters. So how can we do that? Yep, Fischer Esterification. So, yep, HCl and ethanol, and specifically the HCl is catalytic anhydrous. Yep. And there is like one other way you could do this, but this is the most straightforward way, and I think it's usually a good option. Okay, next one, we're taking these esters and we're adding, okay, the facts that I didn't specify actually probably made this confusing. That's my bad. Let's just assume I had put one equivalent. And I guess if you look forward, it kind of helps like make it clear that I was only specifying one equivalent, but you know, yeah, let's just say it's one equivalent. Okay, so we're adding one equivalent of base and then propyl chloride and then acid and heat. So yeah, we're doing, we're gonna make an alpha substituted acetic acid because we're doing a malonic ester synthesis. So you can start by drawing acetic acid, and then we're adding a propyl group. So should add 3 carbons here, make pentanoic acid. Right. And then we're going from a carboxylic acid to an alcohol. So how can we do this? Yep. And then is there anything else? It's 2 steps. The second one is acid. Good question. It doesn't work here because we're starting with a carboxylic acid. Remember, NABH4 only reduces ketones and aldehydes. So that's the kind of thing, like, suppose in that first reaction, if we just wanted to reduce the aldehyde and not the carboxylic acid, then that would be a good place to use it because it wouldn't touch the carboxylic acid, but it would have done this. So just as an example, like of where it only does one thing. Okay. Next, we're going from an alcohol to bromine. We're substituting a bromine. How can we do this? PBr3, yeah. And not as a catalyst, but as a solvent, yeah. And that was actually something I was about to ask about. What kind of reaction or mechanism would this substitution be? like it's a substitution, so it's either SN1 or SN2. Which one is this one? SN2, yeah. Oh, here. That's with PBr3 or SO2 or SOCl2. Yeah, it like primary prefers SN2, so that's why we had to use PBr3 to do this. But like whenever you use PBr3, it's going to be an SN2 mechanism. Or SOCl2. And if you're doing SN2, this honestly usually isn't that big of a deal. Like I don't think there's many cases where the solvent really has an influence in what kind of reaction you do. But just as review, yeah, it should be polar aprotic. SN2 prefers polar aprotic solvents. So ether is a good one. Ether, just to make sure everybody is on the same page. That's a good example of a polar aprotic solvent. It's polar because, I'll draw it up here. It's polar because it has that oxygen. And then aprotic is referring to like having hydrogens that could hydrogen bond. So like water or methanol are good examples of protic solvents because, you know, the hydrogen in alcohols and water can do hydrogen bonding. And then if you have a hydrogen on a nitrogen, that can do hydrogen bonding. So like those are examples of protic solvents. So if H is on oxygen, nitrogen, or I think sulfur is the other most common one, it's polar protic. And if there's not any of those, then it's aprotic. Okay. How about this next one? We're adding tert butoxide and water. Yep, so this is an E2 reaction. And this is only going to be E2 because this is a bulky base. I think Okuda was calling it like an NNB, a non-nucleophilic base. I'm not sure when he started doing that, but it means like the same thing as bulky base. It's just like, because it's a large base, it's not a good nucleophile, so it's non-nucleophilic, but it will be a base. It'll do an E2 reaction, which means it will form an alkene. It won't do substitution. So you get this. And then we want to add an alcohol to the alkene. And we want to add it here specifically. So how can we do that? Yep. Conditions, because we want to form the Markovnikov alcohol. So you want to use those particular conditions. Okay. I'm gonna erase the screen so I can scroll down and go over the last couple of steps. I realize the screen's pretty crowded at this point, so if there's any part of it that like you got lost on and you want me to go over while this is all still here, feel free to ask. Because once I start going over the next stuff, it'll be harder to bring back. You can also watch the recording later. Okay. I can also like fill in any gaps in your knowledge after I finish this, if you did have a question. Okay, so now we have an alcohol and we're adding PCC and dichloromethane. What kind of product are we going to make? A ketone, yeah. This will oxidize it. And how about the next reaction? We're adding a Grignard reagent and then acid. What's that going to do? Tertiary alcohol, yeah, and it's going to add an ethyl group in the process. So the ethyl group came from the Grignard reagent, and then you get a tertiary alcohol. And then last, we're going from an alcohol to chlorine. So how can we do that? So yeah, we have SOCl2 or hydrochloric acid. Remember what I said about the bromine substitution with PBr3? PBr3 and SOCl2 do SN2 mechanisms, right? And what kind of substrate do we have? Tertiary, yeah. So tertiary is not good for SN2. Doesn't really work with SN2 mechanisms. So we can't use SOCl2 just because it's tertiary. Instead, we have to do an SN1 mechanism. And that means you would use HCl instead. And then in terms of the solvent, if you're doing an SN1 mechanism, which we are here, SN1 prefers polar protic solvents. So this is an example of a polar protic solvent with the ethanol. It's just anything with a hydrogen bonded to an oxygen, nitrogen, sulfur, where it can do hydrogen bonding. Okay, so that was also a bit of a review of SN1 and SN2. And that is the whole worksheet. That took, honestly, longer than I thought it would, but that was it. So while that's the end of the worksheet, I'm willing to stay a little bit longer if you guys have any questions or like want some sort of review over a particular topic. Thank you for coming. Hope it was helpful.
I don't have any questions, Nick, but thank you so much for your help this semester.
Thank you for coming.
All right, have a good rest of your year.
You too. Good luck, everybody. Oh, that's nice to hear. Thank you. I know you're all saying thank you and leaving, but like if anybody does have a question, I'll stick around until everybody's gone. But like I appreciate all the like appreciation. Okay.
Nicholas?
I
just had a quick question. So to do you remember the reagents to add like a Br or a Cl to a benzene?
To a benzene, yeah.
Yeah.
So for that, you like if you're adding bromine, you would put Br2 as a reagent, and then it would be FeBr3 as like a catalyst for this.
Okay.
And then if it's chlorine, it would be Cl2 FeCl3.
Got it. And it would just add anywhere, correct? Or like to the benzoic? Yeah, right there. Okay, got it.
If there was something else, like you have to consider the directing effects. So like methyl group would make it orthopara, but yeah.
Okay, got it. Oh, for the chlorine, you said Cl2, and then the solvent was.
FeCl free.
Okay, got it. Thank you so much.
Good luck.
Thank you.